Hi, welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and in this video we're going to talk about continuous compounding. Previously we've talked about compound interest and the compound interest formula, and that formula looks like this. We looked at various examples when we had different compound periods. So for example, compounded annually, semi-annually, quarterly, monthly, and daily. So the maximum number of compound periods was 365 when it's compounded daily. But what happens if n is increased? What if it's more than that? What happens if n gets larger and larger and larger? We know that when we have more frequent compound periods, the money will grow faster. But what happens if n is so large that the money is compounded continuously? I don't want to get too theoretical here, but it was discovered that if we took this expression and increased n to a larger and larger and larger value, it approached a specific number. One way of expressing n getting larger and larger and larger without bound is the limit as n approaches infinity. So as this number gets larger, it approaches infinity, and the limit as n approaches infinity is equal to a special number that's called e. That's called Euler's constant, and this number e is an irrational number. It's approximately equal to 2.71828, but it goes on forever. It turns out that this number is important for a lot of mathematical and physics applications, and one of those applications is continuous growth. And going back to the idea of compound interest, as n gets larger and larger, instead of using this formula, we can use an interest for continuous compounding using e. The formula for continuous compounding interest is this, where future value will equal present value times e, which is this special number here, to the exponent of r times t, where r is the annual interest rate and t is the time in years. You don't need to worry about remembering that value of e because it will be on your calculator. If you take a look at your natural log function here, above it the second function is e to the x. So let's use this formula and answer some typical questions that you may see regarding continuous compounding. Question says you invest $5,000 in a mutual fund that grows continuously on average by 7% per year. What will be the value of the account after 5 years? So in this case, we're finding future value. We know present value or principal is $5,000. We know the annual interest rate is 7%. We'll write that as a decimal. And we know the time in years is 5. So we're going to plug these things into our formula. And in order to find a, our first step is to simplify this. So 0.07 times 5 is 0.35. To calculate this, let's start with e to the 0.35. Enter the exponent 0.35. And then press your e to the x key, which is the second function, ln. So it's 1.4191. And then we're going to take that value and multiply by 5,000. And our future value will be $7,095.34. Let's take a look at some more examples where we're solving for different things other than future value. In our second example, it says an investment earning 6.5% compounded continuously grows to $9,000 in 10 years. How much was originally invested? So in this case, we're given the future value and we're asked to find the present value. Our interest rate is 6.5%, so we write that as a decimal, and our time is 10 years. Let's plug these values into our formula. So we have 9,000 equal to present value times e to the 0.065 times 10. Let's multiply that and just get one number there. Now in order to solve for p, we're going to divide both sides by e to the 0.65. So on your calculator, you can go 9,000 divided by, enter the exponent 0.65 and then the e to the x key equals. And you should get a value of $4,698.41. Our third example says, how long does it take $1,000 to grow to $1,500 if it is invested at 9% compounded continuously? So our future value is 1,500. Our present value is 1,000. Our interest rate is 9%, as a decimal is 0.09. And what we're finding is time. So let's plug our values in. So we'll have 1,500 equals 1,000 times e to the 0.09t. Our first step is to isolate this. So we're going to divide both sides by 1,000. And we have 1.5 equals e to the 0.09t. Our unknown is in the exponent. That's called an exponential equation. And in order to solve exponential equations, we need logarithms. Logarithmic functions are the inverse of exponential functions. And I'm not going to get into a lot in logarithms, but understand that when you're working with base e, that's called natural log. And the notation for that is ln. So ln means log base e. So what we're going to do is take the natural log of both sides of the equation. There's two other properties I'm going to use to solve this equation. One of the properties says that if you have the natural log or any log of a base to an exponent, you can pull that exponent out as a coefficient. So the natural log of e to the 0.09t is equal to 0.09t times the natural log of e. And the other property that we're going to use is natural log of e is 1. So this is equal to 1. So the natural log of 1.5 will equal 0.09t. Now in order to solve for t, I'm going to divide both sides by 0.09. And in order to calculate this, we're going to use our natural log function on our calculator, which is right here. So we're going to enter 1.5 natural log divide by 0.09, and we get 4.505 years. Our last example says, how long does it take an investment that is compounded continuously to double? So we're not given a lot of numbers here. However, if the investment doubles, you can choose any value as your principal or present value, and then the future value will be double that. So let's just pick $1. So our future value will be $2. You could pick 1,000, and then this would be 2,000. Doesn't matter. We don't know the rate and we don't know the time, but we want to find time. So we're just going to leave rate as rate. A is 2, P is 1, E to the RT. 1 times anything is just anything. So 2 is equal to E to the RT. We want to solve for T. In order to do that, we need to take the log of both sides, and we're taking it log base E, which is natural log. So we're going to take natural log of 2 will equal the natural log of e to the RT. Using that specific property of logarithms, I can move this from the exponent position to a coefficient. So the natural log of 2 will equal RT times the natural log of e. Again, natural log of e is just equal to 1. So 1 times RT is just RT. Now in order to solve for t, I'm going to divide both sides by r. So here's our formula for finding time for an investment to double if it's compounded continuously. If I know what the interest rate is, I can just plug it in. So for example, if I had r as 10% compounded continuously, I can find t. I just take the natural log of 2, divide by 10% as a decimal is 0.1. So the time it would take for that investment to double, if it's earning interest at the rate of 10% compounded continuously, would be 6.93 years. So dealing with compound interest when it's compounded continuously is a little bit different. We're using this formula instead of the regular compound interest formula.